consultant here at InCab America, and today we are doing ADSS Engineering 401. So this is ADSS in a high voltage field, theory and practice, and we're going to use a software tool for modeling electric fields and applying that to ADSS engineering. It's 401 because, this is actually kind of an advanced topic. I think it's a topic that doesn't get as much attention as it should. You'll see why in a moment. Some of the preliminary things that we need to get out of the way. This is a RCEP compliant presentation. This just means that we meet their standards for the material content. It doesn't necessarily mean that they agree with any of it. And that upon completion of this, you can earn continuing education credits. This one we rated at 1 hour. And I'll remind you at the end what you got to do to get credit, if that's what you want. So this discussion is going to begin with why use ADSS in a high electric field application in the first place. That's a reasonable question to start with, I think. Then we're going to look at the potential problems that an engineer can face when putting ADSS in a high electric field. And then we're going to give you the tools, how to analyze that and how to solve those problems. And the bulk of that is going to be space potential analysis. And this ACES spot program is just a tool for doing space potential analysis. So learning objectives, so you're going to be able to explain why ADSS is used in a high electric field, state what a high electric field is. You're going to be able to compare and contrast the problems of corona and dry band arcing and what you can do to mitigate against each. You're going to know the difference between space potential and electric field and also why that is important. You're going to understand, well, if we keep talking about electric field, why is it that we then do space potential analysis? I'll explain why. Then I'll show you the theory of doing that. Then we'll actually do it. And then you're going to see how to apply the results you get when you do it. So we've already done the introduction, and if you've heard me thus far, the sound check is okay. Going to take about 60 minutes for the presentation. After that, we'll have chat, but really I think we'll just open the microphones and people can ask questions and I'll respond to them directly. Again, the question and answer session is supposed to be on topic, not discussions about ongoing business with InCab. And let's get started because we got a lot to cover actually. So I already said this, that we're talking about ADSS. This is a 401 level class, so it's advanced. So I'm assuming that you know the basics and perhaps you participated in my ADSS Cable Engineering 101. And if so, then you're going to remember this slide. And this slide said, electric field guidelines. Okay, standard polyethylene jacket limited to 12 kV space potential. And above 12 kV, you have to use a tracking resistant cable and corona coils, and absolute maximum for ADSS is 25 kV, and we'll actually learn that there's an exception to that. But we never, during the course of that class, talked about how you could actually determine what these are in order to apply them. So that's what we're going to do in this presentation. We're going to add some tools to your engineering toolkit. You'll know why you might want to do this. You'll know what the electric field is and what the difference is between the electric field and the space potential. Then you'll learn how to use that information to determine where you can put which type of ADSS jacket on a transmission line so that you get long-term reliability. Okay, so let's start off with that why. And, I actually come from a metals cable background. Some of you that have talked with me know I'm very upfront about that. I worked with conductor and conductor accessories, and then I've worked extensively in my career with OPGW. I actually have a favor or a bias in favor of OPGW over ADSS to begin with. But I'm one of these kind of people that sometimes you got to do what you got to do. And there are some times when ADSS is the best solution. In today's power grid, outages on high voltage and ultra high voltage transmission lines, like 345, 500 kV and above, those are often difficult, if not like on the very cusp of being impossible to get. And so, yes, in theory, you can install OPGW hot, but that runs into some practical problems because of the obvious safety concerns about the induced voltages and currents that you would get on a metal cable like that. So even though it can be done, and there are people that do it, it's not done very frequently. And here in the United States, at a lot of investor-owned utilities, um, there would be a lot of safety concerns that would come up, and you wouldn't find it easy to pitch that to and get it approved by upper management to install OPGW hot. In contrast, ADSS can relatively easily be installed hot. I mean, there's still some things to be concerned about, but being a dielectric cable off the bat, you're not, at least in, well, not just in theory. I was about to say in theory, you don't have induced voltages and currents on the cable. You kind of do, but again, the magnitude of it is such that dealing with the issues of installing ADSS hot is easy compared to trying to install OPGW hot. Another valid reason for doing ADSS is that it is a lot cheaper. So the material cost for it can easily be on the order of half the cost of OPGW for the cable itself, the accessories. And then if you're installing it on an HV or a UHV line, um, and you were trying to keep the line hot, well, the labor costs for installing ADSS will, relatively even widen this gap even more. So even though I really, really like OPGW, I have to concede there are times to use ADSS. And then there's one more case. Sometimes it's effectively the only solution because there are some lines, at least in the United States. I can't speak for all of the world, but there are parts of the United States, in particular the western part of the United States and Bonneville Power Administration's region in particular, where the lines were built without a shield wire because lightning isn't a big issue in certain parts of the country, in that area in particular. And so they weren't built with a shield wire on them. So retrofitting the towers in order to then be able to install an OPGW becomes even more expensive. Not that it can't be done, but again, there's a lot more to it, including a lot of cost. So that was the why. Now the what. So now let's talk about what an electric field is, and let's compare and contrast that with what space potential is. So an electric field is defined as a region of space around an electrically charged particle or object in which an electric charge would experience a force. So basically, the electric charge here is referring to an electron. So an electron feels a force on it, feels the force to move. On transmission lines, that the object, this electrically charged particle or object, is the conductor with an applied operating voltage on it. And that operating voltage itself is the source of the electric charge that's making the electrons want to move. And when we talk about a force or a feeling that you want to move, that implies that there's both a direction on the particle, meaning which changes it into a vector, and over some distance. And we'll talk about why that's important. So what we discover uh, in reality, of course, people talk about voltage and current, and those are abstractions. What's really going on is electromagnetic fields, um, and they are not confined to just the conductor. So if you looked at just a single conductor above ground that's got a 1,000 volts applied on it, just to keep the math easy, you would find that there's a field radiating in all directions around that conductor. That's what you see here. And then we can look at it more closely, and we can start to define some things. So these black lines are the electric field lines. So the an electron feels a force to push it on these lines away from the conductor. These, at any given point in space, if you could go there and you could measure a potential of voltage, that voltage is the space potential. So it's the potential at just one point. But if you find a point that's, say 400 volts, there's 400 volts here, there's 400 volts here, there's 400 volts here, and so forth. And you can connect those with a line that we call an equipotential line. So that's the red lines. Other things that we'll notice is that you go from the conductor at your 1,000 volts to 0 at ground. Halfway is approximately going to be 500 volts. Above the conductor, the field is still trying to go to 0. It's just there's nothing to drive it to 0 like the ground. So this actually continues in theory forever. But you can still see that it takes a certain distance before you've got the field has been reduced by 500 volts. But above the conductor, that distance gets greater. And then if you've had a 500 volt change here to here versus here to here, we can say that the field here is stronger, or the intensity is greater, or it's higher. And that's simply because 500 divided by a larger, by this number is smaller than 500 divided by this number because D1 is smaller. Okay, so basic principles. All right, so the space potential, as we showed, is that electric force measured in volts or kilovolts at any one point in space. So it doesn't have a direction to it, and it doesn't have a distance. By itself, there's nothing. It's just the potential at one point. So the equipotential lines, they are all points at the same potential, and we'll see why later that's of interest and helpful. And the electric field was that looking at the space potentials across a distance with a direction to it as well. Again, a vector. And the unit that's commonly used there is kilovolts per meter. And so when I use the term high electric field, well, that's just a relative term. It's convenient to use the point at which a real world problem starts to occur, and specifically that problem, which again we'll discuss later, is corona. And that point is going to be on the order of 500 kilovolts per meter to 3,500 kilovolts per meter, which is 5 kV per centimeter or 35 kV per centimeter. You'll see both units used. Okay, so that our example to define some terms was a single conductor above ground, but we all know that transmission lines have more than one conductor, right? Well, yeah, of course. And so when you have more than one conductor, or in this, as this picture shows, a bundle of conductors, each conductor's field radiates around it, but then it interacts with the field of the other two. And the fields also interact with the structure themselves. The structure tends to act like ground and drive the field to 0 in its immediate vicinity. So it's distorting the field, which is to say it's changing the intensity close to it. And that's going to be important when we look at corona in particular later. So the added complexity of a three-phase transmission line creates the classic good news, bad news situation. The bad news is the complexity itself. So if you're going to try to analyze what's going on to the towers, your first thought might be, oh, I've got to do a lot of very detailed 3D modeling of the field in order to understand what's going to go on. In particular, what's going to go on next to my ADSS cable that I'm trying to put on this line. And that would be further complicated by the fact that on transmission lines, the geometry changes along a span, right? Because the conductors have sag, the ADSS has sag too, and they don't sag in sync with one another. The sag properties of the conductors is very different from the sag properties of the ADSS cable because they're made with materials with quite different properties. And in addition, uh, so that's just under one given set of conditions. With the conductors, once you put current on them, they're going to heat up and they're going to sag more, which is going to change your geometry yet again. So, and then plus temperature conditions are going to change. Winter versus summer, night versus day. Everything is changing all the time. So 3D modeling would be very complicated to begin with, and then in addition, you'd have to do it under multiple conditions in order to analyze the field and see what's going on. But it turns out that there's good news, and that is that it turns out that the way the math would actually work and how things would be applied in the field, that things get a little bit more simple for us. So if I put a hypothetical longitudinal axis through a structure and look at the field on that, I would actually find that there are a couple of changes that actually help us out. Now, for those of you that are electrical engineers, you'll see that I drew these vectors in this direction. And electrical engineers would say, hey, wait a minute, shouldn't it be the opposite way? And technically, you're right. The way we electrical engineers look at it, we would draw the vectors the opposite direction. But I think for most people, it's a little bit more intuitive to think about um, the field moving from a higher potential to a lower potential, with ground being the structure. So that's why I drew it the way I did. But those favorable changes are the field along the axis is longitudinal to this axis close to the structure. And then as you move to mid-span, it becomes orthogonal, meaning at a right angle to it. And the intensity goes down, not the space potential. The space potential stays the space potential, but the field, if you look at it, becomes smoother. It's distorted by the structure here. The structure acts, and the hardware acts to drive the field to zero, which has the effect of increasing the intensity. The kilovolts per meter goes up. So why is this beneficial? Well, it means that we can look at the problems right at the structure, or problems are likely to occur there. Therefore, that's where we can focus our attention. And it further means that we can simplify our analysis in two very practical ways. Because it's strictly at the structure, we can look at 2D analysis instead of 3D analysis. So we're focusing specifically at the structure, and we can use space potential, so those equipotential lines in particular, as a stand-in for the electric field's intensity. It's like a surrogate, right? And when we think about like electrical safety, we often talk about voltage. Don't touch a high voltage line. But again, for the electrical engineers, we know it's not the voltage that kills you; it's the current that kills you. But the current is a lot harder to know. Like, what's the resist? If I touch my hypothetical 1,000-volt line, is it going to kill me? Well, it depends upon the current. Well, but the current depends upon the resistance of my body. I have no idea what that is. But I can know the 1,000 volts, and I can know, well, 1,000 volts is a big number. That's probably dangerous. And we're going to use space potential in a similar way. Rather than look at the electric field, we can say a high number for a space potential tells me be cautious, that's dangerous. So I said we can look for problems close to the structure. What are those problems, right? Well, there are two for sure, and then a third that we'll talk about later. We'll circle back to it at the end of the presentation. The two big ones are corona and dry band arcing. Corona occurs at the tips of the accessories, and we'll explain why in just a moment. Dry band arcing occurs further out, but still relatively close to the structures. Oh, and I want to shout out to Monty Tominen for this picture. And you'll see his name throughout. And I'll explain who he is later too, for those of you who don't know him. So what is corona? Corona is an electric discharge on an ADSS cable. It occurs at the tips of the armor rods that are used with the suspension clamps or dead ends. Effectively, what's going on there is that the rods are acting to distort the field by quickly forcing it to zero. This causes the field intensity to shoot up. If it gets high, this kV per centimeter gets high enough, it exceeds the ionization limit of the air, or sometimes called the dielectric strength of the air, and then you get corona, this electric charge. It leaks off the tips of the rods into the air, and in the process, it burns the jacket. And that ultimately will lead to catastrophic mechanical failure, which is a fancy way of saying the cable breaks and falls down, and everybody has a bad day when that happens. So you would have to be there when it's happening to actually get a good picture of it. So I couldn't find a picture of corona on ADSS, but I did find this picture. And this little blue light that you see on these corona coils, that's corona. And then for fun, it occurred to me when I found this picture, like, well, why is that happening here? These are corona coils. Aren't they by definition supposed to prevent corona? And well, the answer is that this kind of stuff happens in the real world. If the coronas are designed properly, and I have no way of knowing just from this picture, then it could be that when they were made, the edges were not sufficiently rounded, or that with time, contamination, pollution or salt water has accumulated on them, and now you're getting corona. But it was interesting to me to find pictures of corona on corona coils, and then I myself have seen this on UHV spacer dampers, and I knew for a fact in that instance that was because the dampers had not been made properly. The design was good, the actual manufacturing process didn't leave the surfaces smooth enough. Just FYI. So here's what corona does to a cable. As I said, you get corona discharge. That blue light that you saw in this picture comes off the rods. And in this case, this rod sticking out like that, electric fields don't like things that are sharp or protruded. So it's going to come off of this rod in particular and then burn the jacket in the vicinity. As I mentioned, you can solve this with corona coils. These are what they look like for ADSS cables. They work by grading or smoothing the electric field so that intensity or strength of the field stays below the dielectric strength or the ionization limit of the air. The other solution would be to have perfectly rounded armor rod tips that are installed perfectly evenly, right? So I could say, well, maybe this wouldn't happen if all of the rods were like this one here. It looks nice and rounded. And if they had been installed evenly, uh, and then my response to that is good luck with that. You know, in the real world, things don't get made quite right sometimes, and things often don't get installed exactly the way they should get installed, like you see in this picture here. So we'll see if we can't find another solution. Uh, Dry band arcing, uh, I mentioned, is the other problem with ADSS, and it's basically similar to tracking on insulators. Now, I put a little asterisk here because, again, I know some electrical engineers would say, well, Mike, yeah, but it's also different like this and that. And there's truth to that. But the analogy, I think, is still a valid one to get a handle on the problem, why it's happening, and what you can do about it so that you don't have it. So discussing exactly the differences between dry band arcing and tracking on insulators is beyond the scope of this presentation, but they're similar in some important ways. So it has three ingredients. So you got to have all three at the same time to have dry band arcing occur. You've got to have that high electric field. You got to have contamination on the jacket. So again, pollution or like salt as a residue from salt water. And you got to have moisture. So, um, and here's how that works together. So the cable gets wet and the contamination makes its surface semiconductive. So it actually starts to track. It's conducting a little bit of electricity. And that comes from the capacitive coupling between the cable and the conductor. So in other words, the electric field is initiating that current to flow. That current, though, has effect of heating the water, which effectively causes it to evaporate and thereby dry the cable. But it's not evenly across the cable. So you get small dry bands begin to form. Those bands, when they form, interrupt the current, but you can get a charge buildup. And when the charge gets high enough, it arcs across the band. So basically, you get a mechanism that's basically like a capacitor. And then that arc, it extends the dry band. More heating dries the water, but the arc itself has done tracking damage to the jacket. So again, don't have pictures of that in the field, but I can illustrate that with this sketch. So here's your cable. Let's say it's wet here and wet over here, but a little dry band has begun to form. And you get a voltage across that. The charge is building up. When it gets high enough, it arcs across the band. And then the heat, though, will increase the dry band. So the arcing will stop, but it's already done damage to the jacket. Okay. And another shout out to Monty there. And so here's what that looks like. I don't know your screen resolution, how well you can see this, but if you look at the surface of this cable, it's got these little, looks like cracks in them. And that's where you've had an arc and it's damaged the jacket by burning into it. So the solution to dry band arcing is what's called a track resistant jacket. So tracking resistant jackets, you use a material that's prevents the tracking from occurring. And today, most companies that supply ADSS offer both a standard polyethylene jacket and a tracking resistant jacket. The materials used vary. A common one, though, is to take standard polyethylene and add some anti-tracking additives to it, and those work great. So how do I know if I might have tracking and therefore should use a tracking resistant jacket? Well, again, that's the main purpose of this webinar today. We'll go there. So remember, I talked about where and which. So if you're using space potential analysis, that's going to help you determine where you can safely attach a standard polyethylene jacket and where you can safely use tracking resistant too. Because remember, I said there's an upper limit to the field that you can use a tracking resistant jacket in. And then once you know where you can put what, then you know which cable type to use. Pretty easy at that point. So to review what we said at the beginning, standard polyethylene jackets up to 12 kV space potential. Tracking resistant jacket, 12 kV up to 25 kV. And then a quick reminder, you need to use those corona coils too. There is a possible exception, and again, we'll talk about that at the end. So first, I can go ahead and give you some general guidelines. In theory, you might say, well, you should do space potential analysis for every single application of ADSS, and um, uh, you know, but then the real world hits you. That would be a lot of unnecessary work because up to about 35 kV, the danger of tracking is about zero. So it is zero, not about zero. It is zero. Um, so if you're working on distribution lines, for example, you never need to do space potential analysis. Between 35 kV and 138 kV, you have to try really hard to cause a tracking problem. Now, it's been done. There was a utility here in the United States that somebody got the great idea of putting ADSS within a foot of 138 kV phase conductors, and they did have surprise, surprise, tracking problems, and the cables did fail. But they were putting ADSS really close to phase conductors because, well, it's dielectric, so it should be okay, right? And not realizing there was more to it. Um, Basically, as a guideline, if you use your standard insulator clearance limits, so if your insulator is 3 feet, for example, if you use 3 feet and make sure your ADSS is 3 feet away, you're not going to have a problem. But you could certainly use space potential analysis to confirm that a standard jacket is okay on a 115 kV line, a 138 kV line, or whatever in this general range. Above 138 kV and up to 230 kV, there's a little bit of 161 kV in the United States. You really ought to check. It's not maybe not likely. And again, if you use that insulator rule of thumb that I gave you, your insulator distance as a guideline, and stay away, you're not likely to have any problem. Like, you're highly unlikely, as a matter of fact, to have a problem at that point. But you ought to check it just to make sure, especially when you see how easy we've made it to check. At 230 kV and above, absolutely it is a danger. You not only do you have to use track resistant jacket and corona coils, but you really should do the space potential analysis just to make sure you haven't put a tracking resistant cable in a field that it actually won't survive in. So you've actually got options. Now, I've said we're going to show this software tool that we've developed that we call Spot, but you don't have to. There are Excel workbooks that exist that do this. Monty Tuominen, who I've mentioned already in this presentation, he retired from Bonneville Power Administration, and so he had extensive experience during his career working with ADSS and high electric fields. And he is still around doing consulting. So you could reach out to Monty. He put together a workbook that does space potential analysis. And because BPA was a US federal government entity, you can request a copy from it. It's his work, and they'll give it to you. And I know because I have it. And then we did ACES Spot. The underlying Maxwell's equations are Maxwell's equations. So you get the same result either way. Uh, we like our tool, and we think you'll like it too. So we'll show it to you. So regardless of what specific tool that you use, you've got to start off with your line geometry. So this is just a 345 kV H frame transmission line from that I ran across from one of our customers a few years ago, and the geometry is pretty basic. You got to map things into Cartesian coordinates where everything is. So here, the phases are 1, 2, 3, A, B, C. Here's where they map in Cartesian coordinates. 4 and 5 are OPGW conductors. Or excuse me, 4 is an OPGW, 5 is a conventional shield wire. And because metal can ground the field, you go ahead and include them in your analysis. The phase conductors themselves are Drake, And it's 2 conductor bundles each, spaced at 18 inches. So you'll enter the data, again, whether you're using an Excel workbook or you're using the ACES system, they operate the same. You enter that data, hit your calculate button, and you'll get your output. And then you'll be able to analyze that output. So here, I've got these equipotential lines. So the red is saying that that's above 25 kV. So ideally, I want no ADSS there. This kind of the pink color is where it's between 12 kV and the 25 kV. So I can use a standard tracking resistant jacket in these areas of the structure. I could mount it here. I'm keeping it in the pink. Now, in theory, if I stay in the white area, it means it's below 12 kV. So I, in theory, could use this spot too, but notice that I'm already around 20 feet above ground. So, you know, with a typical transmission line, if the spans are long enough, then the sag of the ADSS might violate code clearance. So I might not be able to do that in reality, but it's good to know that you have the option. So, you know, white, less than 12 kV, so standard jacket, okay. The pink is 12 to 25, so you need the tracking resistant. And then red, try to avoid using ADSS. Okay. So now let's go do it. And give me one moment to call up the program. Okay. Okay. All right. Hopefully you see. I just lost it. Bummer. Gotta be careful. So you should see our website here, and I've already opened the Spot program just to show you what that looks like. So if you start from our main web page, you go to the configurator. That's where we have all of our advanced cable engineering system tools available to you. There's a very simple login or registration process. I'm already logged in. I won't show it. But anyways, ACES Spot is right here. Let's go back. So if you started from scratch, what you would do is, from our diagram, we had 5 conductor bundles. We'll stick with customary units, and we'll say this is Mike's webinar. Example, whatever project name you want. I'd already put in the data, but I'll just re-enter it again anyway. So the Cartesian coordinates, my first conductor was at minus 27 feet relative to the center line and 50 feet vertically. I had 2 conductors. Those were Drake, so they're 1.108 inches in diameter. The spacing was 18 inches. Here, you could either put in the line to line voltage, or if you want to, you could put in the phase to ground voltage. If you put in the phase to ground voltage, it'll calculate the line voltage, or vice versa. But it's usually easier to put in the phase to phase voltage. So I'll delete this next one so that you'll see it. And I'll put in some crazy number here so you see that it'll calculate things for you. The phase, we'll just use 0, 120, and 240 for the 3 phases. So the next bundle here, it was on our hypothetical center line. So the horizontal position is 0. vertically 50 feet again, two conductors, 1.108, spaced at 18 inches, 345 kV, and phase 120. So now I'm at the C conductor, which is over here. So that's 27 positive. Again, vertically 50, 2, 1.108, 18 again, 345, and phase C. My OPGW is here. So that's minus 13.5 relative to the center line. The vertical height is 74 feet. That's just a single conductor, 364 inches in diameter for that particular cable design. 0 because there's no bundle, it's just a single conductor, no applied line voltage, which zeroes out your voltages here, and phase is irrelevant. The conventional shield wire on the other side is positive 13.5, 74 feet. Again, a single conductor. It's a 3/8 inch shield wire, which means its diameter is 0.360. Again, no applied voltage or no spacing, no applied voltage, and no phase. And you get this output to confirm that things look right, right? So like if I had mistakenly typed positive 27 here, something doesn't look right, okay? So I can fix that. And then you hit calculate. And calculate will get you results, like what you saw in the slide just a moment ago. And again, you have it shows you the position of your bundles so that you know where they are. And it's kind of a way of error checking. You can download this as a PDF file. And you get this. It shows you your output, but it also shows you, just as importantly, what all of your input was, what your assumptions were. Okay. Some other features that are available to you is that you can save your results. So I called it Mike's webinar example. Save it. And I can call something back. I also want to show you what's this project code thing here. This enables you to share a model with somebody else. So you copy this information and send it to somebody, and if they then come here, paste it in and open it, they'll get the same data. And so the fact that you can save and open things, it allows you to do all kinds of what if analysis. You know, somebody says, let's use less right of way. So what's the effect going to be if I change the width? And now I have new output to look at and analyze. So you can play around with this, do a lot of what if analysis. You can collaborate with your colleagues and have a lot of fun with it. So we'll go back to the presentation itself. So just to recap, go to our website, basic registration process. You get logged in, enter your data, push calculate, get the results, apply the results. And I already talked about how you can save and open files. And so that really wraps up ACES. Pretty simple, easy. I dare say even a little bit of fun to use. And I had mentioned, and maybe you thought I forgot about microsparking. That term is used in different ways, and so I'm just going to use it as a catch-all. And if somebody feels that this is incorrect, please feel free to reach out and correct me on this. This is my view. It's tracking. Microsparking is just another way of describing tracking when it's occurring on an ADSS cable. And from what I've learned, there are two reasons for that. One is that a jacket is simply in too high of an electric field. And that could be a standard jacket. Of course, that's been more often the case, I suppose, but it can be on a tracking resistant jacket too. So in other words, if you put a cable in an electric field that's higher than it's supposed to be, and using our stand-in space potential values higher, then uh, the cable is going to track, and it's going to be a la dry band arcing, but not really. You know, a little bit of moisture, not even contamination, and some current is going to flow, and it's going to be degrading the jacket, and the cable is going to fail. But that's simply because you put it in too high of an electric field. So it's technically not dry band arcing because you don't necessarily have the contamination and the drying and all that stuff going on. It's just plain old tracking. The jacket is not able to withstand it. So the other possibility is that you've used a tracking resistant jacket, but you've put it in high contamination, pollution. Maybe there's an industrial complex close by, but along with that, there's not a good natural wet dry cycle there. So when a cable is in an area, it could be in an area with a lot of contamination, but if it rains a lot there, you might never have a problem because the rain washes the contamination off, and the kind of the cycle starts all over again. But if you put a tracking resistant jacket in an area and there is no natural uh, wet dry cycle, that pollution can continue to accumulate over time because you're not getting any natural washing. And then at that point, it only takes a little bit of water, foggy day, some drizzle, a light rain, and then you get tracking that's exceeding the jacket's capability because so much contamination has built up. Just a little bit of water makes the cable conduct, and it conducts enough that it's exceeding the tracking resistance capability of the jacket. And so then you say, well, okay, what's high contamination and what's good washing? And that's very experiential. There's some papers about it, and they'll say, well, if pollution is X, that's high pollution. But how are you going to know in the field? How can you measure your pollution or know it ahead of time? Even more importantly, know that you should avoid putting an ADSS cable on a particular area, even if it's tracking resistant. Um, so knowing a pollution threshold, I'm arguing, is not necessarily sufficient to help you do good design for your system. So it's very experiential, but my recommendation is that if you know that you've had tracking issues with your insulators, because they're subject to a similar problem here of too much pollution or contamination accumulating on them, and then tracking and uh, the insulator getting damaged and then failing electrically or mechanically, um, then you're probably going to have the same problem with your ADSS. So then the two solutions is either, don't use ADSS, meaning go to OPGW or some other fiber optic cable solution, or the other possibility is if you are normally washing your insulators because of this kind of a problem with insulators, well, yeah, you can wash your ADSS too. Now, people might object to doing that. It takes too much water. Are you crazy? Whatever. But as a theoretical solution, I throw that out there as a possibility. So microsparking. Now, I also said that there's kind of an exception to this concept of exceeding the electric field capability of your jacket. And it turns out that there's a way that you can kind of cheat Maxwell's equations. You can cheat the field by driving the field to zero in the vicinity of the cable. And you can do that in one of two ways. One is to use a grading bar. So this picture comes from a BPA structure. And again, another shout out to Monty because he gave me this picture and explained this concept to me on some time ago. So what BPA did here is they've attached an ADSS, this is a plain old ADSS AGS type suspension unit with corona coils. But out here, the field strength was still too high for the jacket. But you mount a piece of angle iron here to the structure, and now this angle iron is effectively grading the field of the cable in the area where you could be exceeding the jacket's tracking resistance. And BPA has over like thousands of miles of ADSS installed using this concept, and it works. So they have an extensive track record, haha, pardon the pun, doing this. And a variation of that theme is a corona tube. Basically, it's designed to go on the tips as a replacement for standard corona coils. And this bar down here, so you connect it to the armor rods at the tip. This is basically grading the field so that you don't exceed the field strength of the cable itself. It's still a tracking resistant cable though. But as I say, this becomes a way to extend your range of installing ADSS. And you'll also remember BPA was motivated to do this because they built those thousands of miles of transmission lines without a shield wire at the top. So they were highly motivated to find another solution. Okay, and that concludes the formal part of today's presentation. And I hope that you'll go try our tool online, share it with friends and family too, if you'd like. You know, Thanksgiving is just around the corner. What better thing to entertain your friends and family than some space potential analysis? So now what I will do is oops, I'm going backwards. Here we go. I will open up the floor for questions. So do we have any questions? Let me find the chat bar. Conversation. Aha, corona rings. Okay. Gary Smallin, corona rings, is some corona unavoidable? Is there purpose to move the corona away from the conductor and other hardware? Well, my answer to that question would be, is some corona unavoidable? No, it shouldn't be. If you've done your design correctly, you should be able to eliminate corona. Especially on your ADSS cable. Yeah, absolutely, you should be able to eliminate it. You're either going to use corona coils. Now, I did give you the example of the corona coils on the phase conductor where something was wrong there, but it was not it was not inevitable. The corona rings were either poorly designed or poorly made, or something else was going on there, maybe contamination. But even if there was contamination, I suspect it's either a design or a manufacturing defect on those particular corona coils, and that could have been fixed. And the corona coil, what it's doing is it's grading, which is to say smoothing the electric field. So Corona takes advantage of high electric field, and if you can keep the field low, then you won't have Corona. So you absolutely can avoid Corona by doing something. Even if you had a problem where your Corona coils weren't working, or maybe some mistake had been made and you were having tracking or Corona, well, heck, if nothing else, use Monty's grading bar. You could fix it that way. If you had to. So, okay. Somebody says spot is impressive. This is coming from Denise Fry. That's a high compliment, and I appreciate that very much. Grading bar known as a Monty bar to some. Yeah, I like that. I didn't know that, but I like that. Can Spot model the grading bar? Joe Ronaldon, a great question. Not that I know of. I think by the time you're having to look at grading bars, I think you're forced to look into 3D modeling of what's going on at the structure. Unfortunately, we'll have to think about that, but that's a great question. Appreciate it. What is the impact on human health for the operators who install the ADSS cable? I presume you're talking about during a high, if you were installing ADSS, track resistant ADSS on a high voltage or ultra high voltage transmission line, and they're in the field. So the health effect, the concern that you have, the cable right off the reel on a dry, sunny day isn't going to pick up any induced voltages or current that could potentially be harmful to personnel. But what if it's raining or misty that day? Or again, this contamination or salt spray pollution or something like that. So you would still want to, as for a safety practice, act as if the cable was energized. And if you used work practices as you would when approaching a cable that is known to be energized, you could do it safely. And the field itself, for short-term duration, installing cable, absolutely safe. So it's a matter of making sure that you're following work practices just in case something highly unlikely and very unusual happens. I suppose that's redundant, but just in case, you would use work practices in case the cable became energized. Let's see. Someone can't enable their mic. Sorry about that. We have a couple people that have raised their hands. Oh, maybe I have to enable the mic. I don't know. Let's see. I see Jorge Garcia. So you have a question. If your mic works, please feel free to ask your question. Okay, Joe, you have your hand up too. Did you have a question? You might have to type it if you can't get your mic to work. And Jorge, you're still welcome to ask a question. You can either type it in or if your mic works, feel free. Let's see. Daniel Tominen, the son of the world famous engineer Monty Tominen, said that his dad does have the capability of modeling the components in 3D. And yeah, that's true. With respect to the grading bar, that was a tool that he used to confirm that the grading bar was going to work. And so as I mentioned to people earlier, Monty does consulting, and if you have kind of a unique situation and need or want to take a look at that, reach out to him. And you can reach out to me. I can give you his contact information, no problem. Jorge says his question was answered. That's great. Mic not enabled by you, but I don't see that option, Joe. Okay, I can disable somebody's mic, but I don't see where I can turn it on.
This is Denise, and it's a test. Can you hear me?
I hear you, Denise.
Okay, so it's up to Joe to turn on his mic.
Aha. Joe, it's probably something in your settings. Like if you go look at the top, there's the 3 little dots, and click on that. And then under that, there's device settings. You may not have your microphone set to what you think, or to what it needs to be for you to talk.
Mike, I've got a question.
Sure.
Have you thought about adding a chart that gives, like you gave the example Drake as a conductor, of providing a simple, common used conductor sizes and those numbers in the United States?
Well, when you ask the question that way, the honest answer is no. Hadn't thought about doing that. But I suppose we could, maybe make it like a drop-down pick list to pick your conductor data.
Because the utility, the person that's doing these kind of analysis may know that it's a Drake, but may not have the information readily available on the diameters and all that stuff. So it would just be handy. I mean, I've got one of the old conductor books, but it might be handy to have it on your drop down. It's a very impressive software you've done. Fantastic job.
Yeah, well, I'll talk with our people about seeing if we could add that, because it's a good suggestion. Like you, it wouldn't have occurred to me because I have a conductor book, like as you referred to. So some things don't even occur to you. So good idea. I'll let them know. Joe, I'm sorry we can't seem to hear you. Well, any other questions? Joe, I can only invite you to type in a question at this point, or maybe you and I can talk offline. So, all right. What I heard a voice. Okay, I don't know what the voice was. I'm going to go ahead and close out since we're not able to hear Joe, and doesn't look like there are any other questions. So I appreciate everybody's attention, and I appreciate the questions at the end and the suggestion. If you think of other questions later, please feel free to reach out to me, and other suggestions later too. And please give us some feedback. I mentioned at the beginning that you can get continuing education credits, and the way that works is that everybody who participated today will be sent an email, and the email will have a couple of things in it. One thing is a link where you can click and give us feedback, and I appreciate the feedback. That can be anything. You liked this, you didn't like that. Hey, what about doing a webinar on this? Anything you want. Maybe I need a new pair of glasses, different style, anything you want. I'm open to any kind of comments. But please, I invite you to give us feedback. The second thing is that if you want to get the continuing education credits, there will be a link in there that you click and you go take a test. It's 10 questions, multiple choice. My philosophy on questions is that they should reinforce what was learned. So I don't ask, what was the third word at the top of slide 27? I ask basic concepts and trying to reinforce things in here. So I think you'll find it reinforces what you've learned, and that's a good thing. But anyway, you take the test, you pass with at least 70%, and then we give positive results to RCEP, and they give you the credits. So they actually are the ones who keep track of how much credits people have and where they earned them and whatnot. So that's the way that works. But again, if you have questions about anything to include that, how do you get your continuing education credits, please feel free to reach out to us. There's also a link in the email that you'll get that you can use for that purpose, or you're welcome to contact me. How can we confirm good design for Corona Coil? Oh yeah, we had one more question come up. How can we confirm good design for a Corona Coil? Great question. Whoever designed the Corona Coil should have some test data, and you need to ask them for it. So, because I don't know of a way to tell you how to look at a design or something and say, yeah, that's a good one, or no, that's a bad one. They should have taken their Corona Coil to a lab and done some testing and showed you that it's good for what it's going to do. And that's actually important today, because you don't want to have the situation like I showed in the picture with the Corona Coils that weren't working. So excellent question there. So again, I see some people giving some feedback here, and I very much appreciate that. All the thanks, and it was great, and all that kind of stuff. Really, I do appreciate that. And, we're going to keep doing these. As you see, we try to do a mixture of new ones but come back to topics that we